So alkenes are hydrocarbons since they're only made up of carbon and hydrogen. The suffix is ene. They have at least one double bond in their structure. The general formula CnH2n. They are unsaturated hydrocarbons. Unsaturated means any hydrocarbon that does not contain the maximum amount of hydrogen it can. And it does not have the maximum amount of hydrogen. Even if you simply compare the general formula of alkanes with alkynes, you'd understand that only the alkanes have the maximum amount of hydrogen because they have single bonds, so they are saturated hydrocarbons. On the other hand, alkenes and alkynes are unsaturated bonds, right? If you notice, CnH2n plus 2 for alkanes, CnH2n for alkenes, CnH2n minus 2 for alkynes means alkenes are only one that have the maximum amount of hydrogen in their structure, hydrogen atoms. So they are saturated. The rest two of them are unsaturated. Now, alkenes are usually made from the chemical industry, the oil refinery, which, when trying to complete the gasoline demand because it's too high, and they break down bigger hydrocarbons, heavier fractions, less useful ones, into smaller, lighter hydrocarbons, lighter fractions, more useful molecules by the process of cracking, also produce some alkenes. So what's cracking? Larger hydrocarbon molecules are fed to in sea chamber. Of course, there would be no high oxygen. This is something that they don't mention in O levels, but they do mention in A levels. So you're not skipping the common sense part. Of course, we understand if there is a fuel, there is some oxygen, there is a little bit of a high temperature, boom, it would be an explosion. So no oxygen and combustion should not take place. So the larger hydrocarbon molecule is heated and passed over an aluminum oxide catalyst. Now, if you look back at IGCSE, you'll find zeolite written over there, right? Zeolite itself is not a single catalyst. It's actually a mixture of many catalysts, aluminates or alumina or silicates, a different kind. Sometimes they also involve some natural salts of calcium or magnesium or sodium or potassium. So in case of A levels, we finalize it's going to be alumina alone. But if you write zeolite, that should be also taken as correct. But we still ask our students to stick to alumina. Now, what happens is that there are two possible outcomes which are not explained over here, which were explained back in IGCSE. So it is taken as a prerequisite. Remember, when an alkane is broken down by the process of cracking, it would produce smaller chain molecules and may produce an alkane and an alkene. All right. This is the first possibility. The second possibility, on the other hand, is that when an alkane is cracked, right, it can produce an alkene and another alkene. We write two alkenes because they can be same, they can be different. Most of the time, they are different, and it produces hydrogen. That's the only two possibilities how you can balance this equation in terms of crack. All right. So instead of writing cracking, what do we write? Al2O3, we write heat. I understand we have studied this heat to be at a temperature of about 500 degrees centigrade, but whether you put 500 degrees centigrade or you simply write heat, in both cases, you get complete marks in AS. All right. So notice we have a big molecule. This is decane, and it is converted down into two small molecules, one of which is an alkane, ANE, and one of which is an alkene, ANE. How do we know? CnH2n plus 2, CnH2n. But it can also be two different alkenes or same alkene and a hydrogen. All right. So the low molecular mass alkanes formed are very useful fuels. The low molecular mass alkenes formed are not good fuels as much as they're good for being feedstock. Now, what is feedstock? Feedstock are the starting compounds to make many new products in chemical industry. The top on the list are plastics. For example, think about it. So we start off with the most basic alkene, ethene. You already know previously from IGCSE, we can polymerize it to polyethene. If that's propene, we can polymerize it to polypropene. So you're familiar with small alkene molecules being polymerized to give us uh, polymers that we commonly use in our daily life, because polythene and polypropene products are very commonly used at home and in offices. All right. So apart from cracking of alkenes can also be made by number one, elimination of hydrogen halide. This is chapter number 16. From a halogenoalkane by heating the ethanolic sodium hydroxide, right? And next, dehydration of an alcohol by using a heated catalyst. This is chapter number 17, or by taking a concentrated acid. By concentrated acid, they are specifically talking about concentrated sulfuric acid, which has the capability to dehydrate an alcohol and convert it back to an alkene. So these are two processes which we're going to study in the upcoming chapters. But apart from that, you can convert alkanes into alkenes by simply cracking. Do you know how you can convert alkenes back into alkanes?
Hydrogenation.
Hydrogenation. So I ask my students, then drawing these kind of arrows and giving yourself a mind map that alkanes can be converted into alkenes by cracking, and alkenes can be converted into alkanes by hydrogenation, is a very good way to do it. That's why we give mind maps to our students specifically for organic chemistry, so that you have an idea about which process to proceed with in case to form what product. All right.
Yes.
Okay. Moving on. Now, let's clear this out. Addition reactions. Let me clarify a little bit. Back from IGCSE, you are familiar with three addition reactions. The first one is hydrogenation, reaction with hydrogen, or sometimes we call it addition of hydrogen. The next one is bromination, or we may also call it halogenation, in which we react an alkene with bromine. This was also considered as bromine water test, which is one of the most famous unsaturation tests we have been through in IGCSE. Lastly, hydration, addition of water. All right. So these are the three addition reactions you're already familiar with. Instead of three, what we're going to do in AS is that we're going to go with a total of five addition reactions along with the mechanism. So hydrogenation is there, bromination is there, hydration is there, hydrogen halide addition is there. So we need to understand these along with the mechanism which we are going to call electrophilic addition. Now, before we move any further, electrophilic addition is pretty simple. I tend to start with B first instead of A because B is the one that is simplest. Double bond or alkene, convert that double bond into a single bond. Keep the atoms or group of atoms at the diagonal and add this molecule, sorry, two atoms, uh, equally by adding one of these on one carbon atom and the other one on the other doubly bonded carbon atom. This is going to be extremely easy. You break one of the double bonds and you break this entire bond. So addition is pretty easy. In case of these kind of atoms, now remember, just a minute. All right. So in this case, XY, again, do the same, break this bond, one of the double bonds, and one of the atoms on one carbon atom and the other one on the other one. It's as simple as that. We are going to get it complicated in the upcoming pages by adding Markovnikov's rule in there. But before we do, that's how it's going to proceed. Now, the examples previously have been easy and actually inform these. For example, hydrogenation or bromination are a very good example of easy. And for the example of XY, water is a perfectly good example. This is what you have studied so far. So let's move ahead. Let's see what we can do about these reactions process by process. Okay, so moving on. First of all, addition of hydrogen or hydrogenation reaction. So hydrogenation is mentioned over here. Hydrogen gas and ethene are heated and passed over finely divided platinum. By looking this word over here, what we use the same phrase back in ICCSE for Haber's process, catalyst, iron, I hope you understand and remember that we don't use the word powdered or ground or fine with metal. With metal, instead of using the word powdered, we should use the word finely divided. So whether we're talking about iron, platinum, or nickel, or palladium, whatever that is, finely divided. Apart from that, what this book does not cater, and you'll find in reference books, is that when we use platinum or palladium as a catalyst, we do the reaction at room temperature. And when we use nickel as a catalyst, we increase the temperature anywhere from 200 to 300 or 150 to 300 degrees centigrade. So instead of putting all of this over here, there, actually go with either this one or this one. All right. So make sure you add a little bit of bifurcation in there. For margarine, one extra line would be very good. That is actually a word reaction. So vegetable oil plus hydrogen gives us margarine. And again, use the same conditions over here. Whichever one of them you're implying, actually, I'll be honest, platinum and palladium are very expensive catalysts. So we tend to go with nickel. Even with nickel and the fuel cost for 200 to 300 degrees centigrade added, this still is cheaper than platinum. So the industry tries to go with nickel. That's how margarine is produced. Although you should never consume margarine, that has no good nutritional value. But again, what is actually margarine? Now, let's go with this. Unsaturated oil. Now, remember we studied a chapter of esters back in IGCSE, and we clarified that the esters exist in two different forms naturally. They exist as solids at room temperature, or they exist as liquids at room temperature. If they exist as solids, we call them fats. If they exist as liquids, we call them oils. Remember, oils and fats as a whole in biology are known as lipids. Don't forget the word. This word is taken from biology and also used in chemistry as well. Now, the solids or fats because they have actually more saturation in them, more single bonds as compared to double bonds. And the oils are actually oils because they are fairly unsaturated. Now, what we do is that we do not completely remove that unsaturation. Let's suppose a chain has 17 carbon atoms and it has 4 double bonds. We will not remove all the double bonds. We'll add hydrogen. We'll straighten their hydrocarbon chain. This would raise the melting point of oil, change it from liquid to soft solids. We can spread them easily, and they are partially saturated. Some of the double bonds are converted into single bonds. and we can convert the liquid into solid or the oil into fat, hence vegetable oil to margarine. I hope you get the point now. There have been hardly one or two questions related to this in the past papers, and they are the old, not latest. But since there are questions, we tend to explain these to the students. I hope this clarifies it. Moving on. Addition of hydrogen lights, HX. This is new. This isn't something we studied back in IGCSE. So yeah, what we can do is that we can take a hydrogen halide and we can react for that, but you have HF, HCl, HBr, HI. In this case, an alkene will be converted into a halogen and this is an addition reaction. Now remember, the very definition of addition reaction is that the compound is added to another compound, but there is a single product. Now, in this case, we are supposed to go with Markovnikov's rule. Markovnikov's Russian scientist, as the name suggests, equal to or more similar to Kalashnikov. Well, that was also a Russian name. Now, longer asymmetrical kenes, there is always two possible products. Now, let's talk about what asymmetrical kenes are. Asymmetrical kenes are alkenes in which double bond has different chain lengths on both sides. Imagine this chain. Now, this is 2-butene or but2ene. Now, if you look at both the sides of double bond, they would have exactly the same structure on both the sides. This is symmetrical kene. Means the double bond has the same structure on both sides. Double bond has CH on both sides, then a single bond on both sides, then CH3 on both sides. Let's talk about but1ene. Now this changes everything. Look at the structure of but1ene. Look at the double bond. You'll see that the double bond has CH2 on one side and a 3-carbon chain, CH, CH2, CH3 on the other. So this is totally an asymmetrical kene. Now for asymmetrical kenes, there are two possible products. One of them is a major product. Major product is usually the product whose production percentage is anywhere from 80 to 95% or more. Minor product is the product that is produced in far less amount, which is usually 5 to 20%. Hence the words major and minor. Now, how would we know that which product is major and which product is minor? Since that's not applicable to symmetrical kenes and they always give the single product, so let's erase this one. Now, if you look at it, there are two possible options that we can go for. Either I can add, and I'm going to use a different color for this one, H onto this side and Br onto this side. What would I get? I would get CH3, CH, Br, CH2, CH3, right? There is another option. I can add Br to this side and H to this side. And of course, that way I'd get CH2, Br. I'm going to quote Br over here. And then CH2 again, CH2 again, and then finally CH3. If you look at it, you'd understand that one of them is bromobutane. And if I be specific, 1 bromobutane. And the other one is 2 bromobutane. In the similar way as the book 1 bromopropane, 2 bromopropane. Now, one of them is supposed to be the major product. One of them is supposed to be the minor product. Before I move any further, look at the name. Look at the structures. Remember the topic isomerism back from chapter number 14. These are position isomers. The isomers are the same. The functional group is the same. It's just that the position of the functional group on a different carbon atom in both the isomers. In one of them, it's 1, and the other one is 2. So we get position isomers with asymmetrical kenes. Now, definitely, there should be a way of understanding that one of these positions are going to be better than the other. All right. Okay. So let's go with the important rule. Where two addition products are possible, the major product is the one in which the halogen atom is bonded to carbon-carbon double bond, or and the specific carbon atom, which is the highest number of alkyl groups bonded to it. Look at this one. This one has one hydrogen atom, and in this alkyl chain, this one is bonded to one alkyl group. Look at this one. This one has two hydrogen atoms that's not bonded to any alkyl groups. So the bromine would prefer over here. This is going to be, and I should use a different color. This is supposed to be your major product. All right. And this is supposed to be a minor product. Now, this is the reason that the book quotes highest number of alkyl groups. What we usually tell our students as a tip is that you can look at the number of hydrogen atoms. Lesser the number of hydrogen atoms, the more preferable is that the halogen or the more electronegative atom would tend to go to for a major product. All right. Look at both the carbon atoms. One of them has one hydrogen atom, the other one has two hydrogen atoms. The one that has less number of hydrogen atoms would definitely have more alkyl groups attached, and hence the more electronegative atom, on in this case bromine, is where it is going to go to for the major product. So of course, in this case, this one is the major product and this one is the minor product. I hope this gives you the idea. Now, whether you pick the point of counting the alkyl groups and attaching the more electronegative atom or the halogen atom with the highest number of alkyl groups, or whether you go with hydrogen atoms and connecting the more electronegative or the halogen atom to less number of hydrogen atoms present, both ways you're going to get your answer correct. Now, there are some past paper questions which can be a little bit confusing. For example, this seems to be an asymmetrical key. And yes, it is, because on double bonds, the number of carbon atoms are different on both sides. One has two carbon atoms on the other side, and there is one on the one side. So if you look at it, you'll see that this is an asymmetrical key. You can go ahead, you can go for a major and a minor product, but this gives us either 2-bromopropane or 3-bromopropane. But in both cases, it's going to give you the 2 or the 3-bromopropane as your product. So you won't be able to come up with a major or a minor product. Why? Both of them have same number of hydrogen atoms. Both of them are connected to same number of alkanes. If that happens, consider going for the same product or both the products at the same rate in the equal amount. This can be confusing question, but that's how it's answered. And you'll find the
So
same answer in the past papers.
won't the 3-bromopropane be more like the major product?
No, actually, there are other effects that come into play, and since we do not explain any effects apart from inductive effect at this level, so we stick to both products as the same one. As I mean, none of them can be called major and none of them minor at this stage, because we stick to just inductive effect. I've seen teachers explaining field effect as well and then talking about it, but that's not a part of it. And also, you won't find it in marking scheme. You'll find the answer I'm telling you about in the marking scheme. So why not go with the method the Cambridge actually picked, right?
Yes,
And
sir.
that's a separate discussion, that two or three, which one is more favorable. And yes, one of them can be more favorable than the other. But there are other reasons in play. Okay. So moving on. Now, we need to explain this. How do we explain it? Now, the one that is the major product, if you look at it, this was our major product. And I'm going to go ahead and draw this, our 2-bromobutane again. If I remove the bromine out of it, then I get a carbocation. Look at this carbocation. This is a secondary carbocation. In the other case, our minor product, was this. And if I convert it into a carbocation, this is what it would form. Now, this is a primary carbocation. So in case of 2-bromoprotein, we have a secondary carbocation, and in one, we have a primary carbocation. Remember, if I compare carbocation, and back from chapter number 14, primary carbocation is least stable. Secondary carbocation is more stable. And the same thing is mentioned in the book over here. All right. So the major product is this one, a secondary carbocation. And this is what gets confusing about 2 and 3-bromopentane for the previous example I was talking about. Both 2-bromopentane and 3-bromopentane, if we convert them into carbocations, both of them are secondary carbocations. Though there is still differences, I'm not saying that this is not solvable, but since we don't talk about any other effect apart from inductive effect, and we don't even compare inductive effects for different alkyl groups, so we stick to the answer that I've told you before. Okay, so that's how we talk about it. Remember, secondary carbocation would be more stable because of having a positive inductive effect of 2 alkyl groups rather than just one. So that would actually go for the major product. Now, the mechanism consists of these 3 steps. A carbocation forms, attacked by a negative ion after, finally gives us the addition reaction product. So if I go with this, it's pretty easy. That's how it goes. Since there is more electron density over here than any other singly bonded structure, any other single bond in the entire structure, this attacks the electrophile, partially positively charged species. The nucleophile then tends to keep the entire bond towards itself and hence is then converted into a negative ion. This produces this negative ion. This entire structure, this entire portion produces our carbocation. Negative ion attacks the carbocation in the second step, as mentioned above. And finally, in the last step, we have our product for the addition reaction. Now, if you look at the past papers, you would notice that marking schemes or sometimes even the question papers specifically mention you need to put up curly arrows. Curly arrows are the arrows which actually tell us how the attack should proceed or why or what reason is behind that attack. I know the derive for being or giving a more stable product is most of the time a derive for the entire reaction, but that's not how it starts. It most of the time starts with electrophiles and nucleophiles, where high electron density portions are attracted for electrophiles, being partially positively charged or completely positively charged, whatever the case may be, or sometimes a partial positive center or a positive carbocation center is attacked by a nucleophile or negatively charged species because they get retractions, right? So most of the time it is going to start because of the presence of charges, partial charges, lone pairs, electrophiles, nucleophiles, however you'd like to name it. Make sense?
Yes, sir.
Now, after doing this, remember this applies to our example of hydrogen halide. But you'd notice this never applies to hydrogen. You will never have to do the mechanism for hydrogen. But any example, hydrogen slides or after, you'll have to go through with this mechanism. For example, the same mechanism applies to water. It's just that in case of water, we won't have Br, we'll have OH. And of course, we won't have an Br, we'll have an OH negative. And of course, no Br, OH, which means we're going to produce an alcohol in case of addition of water. But water is not added as such. Instead, we add it in the form of steam, hence the G. Now, steam, gaseous alkene, high temperature and pressure. Now, notice A levels is not even quoting the temperature and pressure. Back in IGCSE, you quoted a temperature of 300 degrees centigrade. Back in IGCSE, you quoted a pressure of 60 atmospheric for specifically the reaction of ethene and steam to produce ethanol. So, since this is a generic one, they don't even quote the temperatures and pressures because for bigger chains, it's definitely going to be different. That's what you're supposed to do. Okay. The catalyst is phosphoric acid, phosphoric 5 acid, proper name, produces an alcohol. This is a method of converting an alkene into an alcohol. Now, for the symmetrical alkene, the alcohol produced is perfectly easy. I hope you understand it from here. But for asymmetrical alkenes, remember there is a major and a minor product, and major product would be the one where there are chances of a more stable carbocation. Let's take an example of prop-guanine. Now, if we're talking about this, remember, nothing happens to the saturated portion of the chain. Everything that happens to the unsaturated portion of the chain. So it's that easy. I actually take out one of the bonds and then I can either add H over here or OH over here, which is 2-bromo, oh sorry, uh, prop, propane 2-ol. All right, let's write the name for our own ease and understanding. On the other hand, if I talk about the minor product, I'm already taking out the second bond out of it. So if I add OH and H, this is propane 1-ol. Remember, this one is major product since it hints towards more stable carbocation, and this one is a minor product since it hints towards a less stable carbocation. Make sense?
Yes, sir.
All right, good. Moving on. Next up, we have addition of halogens, which includes fluorine, chlorine, bromine, and iodine. Remember, the reactions of fluorine are very explosive, whereas chlorine and bromine react vigorously but not as explosive. Iodine reacts in a slow reaction. The reaction with bromine is commonly taken as a reaction for unsaturation. Why? Because bromine has a yellow-brown or orange-brown appearance in bromine water or dilute solution. Remember never to quote it as red-brown if bromine water is aqueous or usually which most of the time it is or it's dilute. Remember the red brown appearance is the appearance for bromine. The more you're going to dilute it, the color is going to go pale. So if there is dilution, go for orange brown. If there is more dilution mentioned in the question, go for the yellow brown color. Don't keep writing red brown all the time. Now, we can also take chlorine water. It's a pale green solution. Bromine water, orange and yellow, depending upon the concentration, as I just explained, but never red brown. Okay. And if the test is positive, it would be decolorized to colorless, which tells us the presence of unsaturation. Now remember, I have been using the word unsaturation, which means The test can be conducted for double bonds, as mentioned in the book over here, or can be conducted for triple bonds as well, which is mentioned in your revision book, not this book. Which means if he goes with a different question and picks up an alkyne, yes, the test would go positive and it would convert, decolorize, and it would still give us a hint for unsaturation. Keep that stuff in mind. If you want to note it down in the book, do go ahead with this. So the mechanism of this electrophilic addition, we are done with the mechanism. This should be easy. This specific one, in this specific one, we have a couple of things to understand. Now, BR-BR bond, this specific bond is non-polar in nature. Now, you must be thinking, how come one BR is partially positive and one of them is partially negative? This BR-BR bond stays non-polar when it's in normal range, or you say it's far from ethene. As soon as this molecule gets closer to an unsaturated molecule where we have a high charge density of due to the presence of more electrons than usual, as soon as it would come closer to this would act as a polar bond. Why? I'm going to compare it with the bonding chapter ID-ID forces. If you remember, in case of ID-ID forces, the perfectly shaped molecules, when came closer to one another, because of the electrons present in their outer shells, and in center we had the positive part, so the center is positive, the outer portions are negative, these would start repelling one another. And we remember that they were D-shaped like this, positive side over here, all the negative on the other end. Of course, positive side over here, all the negative on the other end. They are D-phase. The same thing happens to bromine. This portion becomes smaller. All the electrons go a little bit away from here because of the high charge density of this. And again, this also dephases and the electrons go over here. Now, since this one has more electron density, partial negative, this one seems to be deprived of electrons, partial positive. As soon as it becomes partial positive, this tends to attack on this one, taking it as an electrifier. And all of this happens instantly. Hence, the proceeding, and then the proceeding is pretty normal. You get one bromine negative ion, one bromine is attached to it. It still forms a carbocation. Negative ion acts the carbon cation in the center, the positive part, and there you go, you have a product. Make sense?
Yes, sir.
Now, I'd like to clarify a few things. Remember, we are done with not 5, 4. I made a mistake saying 5 in the start, but we are done with 4 addition reactions. Now remember, when we are adding hydrogen, we are converting an alkene, and all of these reactions are for alkenes. The alkene is converted into an alkane. The second one was HX. In case of HX, it is converted into a halogenoalkane. All right. In case of steam or water in the form of steam, of course, it is converted into an alcohol. And in case of X2, the halogens themselves, they're converted into dihalogenolcanes. Now, there is a difference between both. In halogenolcanes, we tend to have one halogen per molecule, but in case of dihalogenolcanes, we get to have two halogen molecules, atoms per molecule. All right, keep the difference. Keep this stuff in mind so you know and you remember which reaction produces what. Are we good?
Yes, sir.
All right, great. Now, the big mapping questions are usually the ones that ask for this kind of stuff. Oxidation of alkenes. Alkenes are usually oxidized by powerful oxidizing agents such as acidified potassium manganate 7, and the same reaction can also be carried through acidified potassium dichromate 6. right? Keep that in mind. Usually we go with manganese 7 and the questions are asked in the similar way. Now, remember that we have two different conditions. Under cold dilute acidified condition, it produces a different product. And under harsher conditions, such as hot concentrated acidified manganate, they will give a different product. Starting off with cold dilute solution, of course, since the word dilute is there, I hope you understand that water is going to participate in the reactions apart from the oxygen that we're getting from the oxidizing agent. An alkene would be converted into a diol. Now, diol clearly represents there would be two alcoholic functional groups in there. Now, that's pretty easy. One OH, another OH. That's how we divide it. It's easier to understand this way. So one OH goes to one carbon atom and the other OH goes to the other carbon atom. That's how easy it is. The rest of the chain, nothing happens to the rest of the chain. This is also a test for unsaturation since pale purple color, it's cold dilute. Of course, it's going to show pale purple color and not dark purple, will turn colorless. Sometimes instead of pale purple, they use the word pale pink, means the same thing. It's also a test for unsaturation, which means this would go true for double bond as well as triple bond. All right. So moving on, hot concentrated has a whole big mind map because this produces multiple products depending upon the type of atoms or group of atoms that are attached on the diagonal alkene portions. Now look at the alkene. If both of them are hydrogen, it's going to produce a carbon dioxide. This whole double bond would be broken. The carbon will be oxidized to produce carbon dioxide. And of course, these hydrogens will be oxidized to produce water. Since we're only talking about the carbon-based products in this portion, so we're not actually considering what's going to happen with these three dots. These three dots means what's present on this side or the other products in the reaction. But sometimes students tend to forget the fact that this is also going to produce water, sorry, not hydrogen. Hydrogen would be oxidized to water. So if you're asked to write the complete equation, make sure you write it correctly. The other option is there is an alkyl group, there is hydrogen on that carbon atom. That's pretty simple. Break the whole thing and double bond it with oxygen. That's an aldehyde. In the next step, this hydrogen is simply converted into OH. This is a carboxylic acid. And in this case, which is the only case over here, further oxidation is possible. Happens inside the system, then in there. If you don't take out the aldehyde properly, it would quickly convert into a carboxylic acid. How do we take it out? I'm not going to discuss it at this chapter. This is going to be the part of next chapter. Although the discussion will be completed in chapter number 18, but we're going to start discussing the method in the next chapter. The last option, two alkyl groups. Maybe those alkyl groups are same, maybe they're different. That's why R1, R2. Now, break that double bond, simply connect it with doubly bonded oxygen. There you go, you have a ketone. In both cases, 1 and 3, no further oxidation is possible. Carbon dioxide cannot be converted into any other oxidized product ahead of it, and so is a ketone. Now, the book clarifies with very good examples. Let's cater a few examples. Take a look at this example. Now, as soon as you see a name or a formula written like this, I always insist my students to convert it into a diagonally shaped portion so that you can properly assess what product it is going to give you. So on one side, we have two hydrogen atoms. Of course, we're going to convert it into a CO2 plus an H2O. On the other side, we have two R groups. Both R groups are same. So we're simply connecting it to oxygen. Makes sense. It would be a ketone. So one of them is a ketone with the same structure as I've explained. and the other part gives you this. I hope that makes sense. So a simple one, let's clarify it. A simple alkene like this one would give you two carbon dioxide. Of course, it's also going to give you two water molecules, and you shouldn't be writing it as CO2 plus CO2. Two CO2 would do the trick for a complete reaction, but that's not what they are intending to do over here. They're intended to tell you the products only. Think about CHR, CHR, it's going to give you two aldehydes, and finally two carboxylic acids, which may or may not be the same. R1, R2, R3, R4, two ketones, again, may or may not be the same, depending upon the R groups. So that's how it goes. Now, just for the sake of practice, let's consider this. What is this going to produce? And then what is this going to produce? Let's discuss the first, the one on top first.
Ketone
And
and water. Ketone and carbon dioxide and water.
okay, the one on top is going to give you a ketone, and let's discuss the one on top again, because I think you're making a mistake. Try again.
Sir, aren't we going to get propanone and ethanoic acid? The first one. And then it may be further oxidized.
Propanone, and the second one is repeated.
Ethanoic acid.
Ethanoic acid. Okay, good. I thought you said methanoic. That's why I was confirming. Yes, that is right. So if we take this one, this part off, break the double bond, that's the first step you need to do. So we have this and doubly bonded oxygen and this, right? This is propanone. If you don't remember the naming here, don't worry, we'll cover it in chapter 18. For this part, this is going to be CH3, and remember the CH is converted into COOH, hence ethanoic acid. Let's talk about the one at bottom.
the butanol and methyl acid.
It won't produce an acid.
So
And you're
carbon
correct
dioxide
with,
plus water.
yes, butanone. This whole thing is going to produce butanone. Break it down. Portion over here, functional group, gives you the butanone part. And of course, this one would be converted into carbon dioxide and water. There you go. Are we good?
Yes, sir.
You too? Still confused?
Sir, how do we break these and then form the product?
First of all, break the double bond, because that's what happens, and that is even explained at the very start of this. If you go back a few lines, under harsher conditions, the double bonds in the alkene is completely broken. That's the first thing they explain over here. There you go. All right. So the first thing you need to do is to break the double bond. That's what happens. Okay. As soon as you're done with that, if you have two R groups, simply add a double bond oxygen to the carbon that was doubly bonded. This would give you the ketone. On the other side, whatever you have over here, it would definitely would be CH and a carbon chain. So convert that CH into COOH and the carbon chain remains. You get the acid. And the one below, again, the whole thing with two R's remain the same. Just the singly bonded carbon atom or the doubly bonded carbon atom would now have a double bond with oxygen. Again, a ketone. You have a ketone right here. And the CH2 is simply converted into CO2 plus H2O upon oxidation, because carbon oxidizes to carbon dioxide and hydrogen oxidizes to water. Make sense?
Yes, sir.
You should practice more questions related to this one from the topicals. This would give you much better idea. And this is present as a part of paper 1 as well as paper 2. So you can pick up any of those papers for practice. Okay? Because paper 1 would have the compounds written like this. And many confusing options are there. Since only one of them is correct, the rest are there for confusion. So you'll have a very good practice. Go ahead and practice this one. All right? Let's call it a day then.